topic is Lempel Ziv encoding technique. This is also a compression. Okay, you can call encoding or a compression technique. Right. So normal application could be the text, whichever you, if I want to transmit the textual data from one location to other location using any technique, maybe internet or right, whatever you want to save it in a drive and you take it to other place and then you extract. Right. Whenever we want to do such an operation, we need the concept of what is called as a compression, right? I want to compress. So compression happens by performing an encoding, right? So that's going to be performed using the following steps. The Lempel Ziv, right? As I saw in your syllabus, there are many other techniques before this, maybe Huffman coding or right. So many other techniques are there, right? This is one addition to that. Okay, so again, if you go in very detail, you will see that this has more advantages compared to maybe Huffman, linear codes, etc. Right? Okay, so we'll first look at the steps that we are going to follow, and then we'll start solving the problems based on this. Okay, so again, if you want to come to the basics of this encoding schemes, right? You convert the data into any other format. Basically, you are transforming, right? For example, if I have a letter A, I may write it as 10, right? So in the sense, this is actually a transform. So a transform is valid only when you have an inverse possible. In the sense, if I'm doing an encoding, right, for a text, I convert into some data that's called as a transform. You do encode, right? You are performing the encoding algorithm. You are applying an encoding algorithm to the data. It is valid only when you are able to come back. In the sense, I give 10, you should be able to come back to A, right? Only if that is possible, then we are going to call it as a right proper transform. It's a well-defined transform. Okay, right. So that's very much necessary. So the word transform, even you may hear in some other fields as well. Okay, not just related to this. Maybe you might have heard say Laplace transform, Z transform, Fourier transform, etc. They are also the transforms because you're converting from a domain to other domain. They are time to frequency, right? Fourier will be doing that, but it's a well-defined transform because you are able to come back, right? Frequency is given. Yes, I can take the inverse of that representation and I can come back to that. So you see, it's related everywhere. Wherever we use the words, they are related. That it's the meaning is ultimately same. Okay, so let's look at some of the steps that we are going to follow to do this encoding or a compression scheme. All right, so first we start, a data will be given to you, right? When we solve the problem, these steps will become easy for you, but I'm writing the steps just because I want you to go through this, and if at all a theory question comes, you should be able to write what you are doing. Okay, so there are two possibilities. One, explain how do you do the limples, maybe a short question for 3-4 marks or something, like just 4 or 5 points you should be able to write, so that yes, theory is also covered. Then one obvious question will be, okay, perform a encoding. That's next possible question. Given data, perform a encoding. So yeah, next part of the question will be perform a decoding. They may give a encoded data. You should be able to tell that, okay, this is the message that is present in this data. So three fundamental questions possible in Lempel Ziv. All right. So so start the process. First, what we do, we try to partition the given data. Okay, start the process by partitioning the given data into variable length blocks. All right, so there is a name. If you refer some of the textbook, they call this by a name that's called as LZ parsing, SING. You simply cut the given data, right? According to some rule. Now the rule I'm going to mention in the next point, right? So if a data set is given, you will see that there are varieties of questions possible. Either the data contains ones and zeros, the binary, or even the numbers are possible, 0, 1, 2, 3, right, etc. The they can be present, or even the letters can be present, like A, B, C, D, whatever, right? So we always have a sequence of first I'll write bits, it's possible, or even you can have numbers, or you can have the letters. This may be the given data. Okay. uh, okay, a sequence of letters are parsed. So the previous step, the word parsed has been used, so I can directly use it, right, into groups. This is the first step. So when you do the grouping, you should take care that uh, these groups are the shortest subsequences, in a sense, right? They are the shortest possible groups. That's the first thing. And they should never be encountered earlier. I am forming a group means that group should not be present earlier. Okay, right. So that's the first and the foremost rule to be followed. Okay, I'll add that point into the groups uh, that are the groups are shortest. Okay, they are the shortest, and they also and are never encountered uh, before this. So I can write early. So whenever I do that, I should take care of this. Okay, then so in the next step, so that will be my first step, right? When I do this in the next step, let me assume I consider bits for our representation. This can be definitely extended to numbers or even the letters. Okay, for the simplicity in this explanation, I'll use the bits. Okay, I assume that given data consists of bits like 1010111000, some data I have. Okay, sequence of bits. Okay, right. Now, the idea is that I will try to encode every group starting from the first group, right? So some data is there, 101100 something. Let's assume that I split into the groups as such, like this, maybe. Okay, so these are the groups, let's assume. So I give a encoding to this. I give a different encoding to this because my first two data are different. But when I come to 1, I can see that I can use a coding technique, or the code which I already have used can be applied here because there are two ones possible, right? Make that makes sense, right? So if I get a group which has a part that is already being used, right? Why don't you use the code that has been already used for that particular data, right? So I don't have to create a new data for this. I can try to use the previously existing data, right? So in this particular Lempel Ziv method, we are trying to see, since you are all using what is already existing, so this data is considered to be compressed. This 1 I can try to use already existing something over here, right? That's what is called as a compression. All right. So I'll try to write I'll bring a new word now. I have not used in this explanation, but anyway, when I write, I'll use it so that it becomes easy for you to understand. Okay. So in the LZ, Lempel Ziv encoding, uh, okay, the compression happens uh, by using a coding or encoding technique that uses, right? I'll write, say, some. It uses some previously used, previously used code. It's also referred as code or string. Okay, so there is a name called prefix. There is a prefix term coming. Now you will see when we solve a problem. Okay, and so you see I'm using which is already existing, so I don't have to create something new. I can reuse. So that actually reduces your code size. So you can see that something is getting compressed over there. Are you comfortable with that word which I use? Okay. Yeah, one is prefix. Prefix in the sense it's already being used. I'm using it once again. Okay, reusing it. So I don't have to create a new thing here. So that saves something. You can call it as a compression. Okay. So and then addition to that, I'm going to use a information bit. Okay. So and information bit that is present for the current data. Okay, so I had 3 or 4 sections. Okay, to this section or to this group of the code, I used a previously existing code for one part. Maybe at the end I have one bit which is not there in any of the previous groups, so you see that I have to do an encoding of this one, for example. Okay, so I'm going to call that as an information bit, or some of the textbooks will all call it as a innovation bit. Okay, so and an information bit, or it's also called as innovation. That's new to you. Okay, so that's why it is innovation or an innovation bit. Right. So now you see, I used, you see, this is variable length, correct? So, sorry, not information bit. This information or innovation bit is a single bit, but whatever I use as a previous is variable, right? So ultimately, you see that you are going to get a variable length of sequences. Okay, now this particular whatever we generated so far is actually going to be called by a word called phrases. Okay, so I'll write one, the variable length of blocks are referred as phrases. Okay, so anyway, I'm not going to use this in when I solve the problem, but the steps we refer in the textbooks, they say that okay, all these words are there. Okay, fine, let's proceed further. Now I have the variable length of blocks, or you call it as a phrases. What you do in the next step is that store these phrases in certain dictionary. Okay, so I have to create a dictionary. This is the next step. The upcoming step after we do this splitting up of the given data into several blocks is that I'm going to store the phrases into the dictionaries. Okay, right. So these phrases get stored in a dictionary. All right. So how do you store? You don't store as it is, right? In the form of the existing phrase, right, plus a location. Okay, I'm going to show you this when we solve the problem. Okay, what there is, so the procedure is very simple. Okay, only 3 steps are there. So this was the second step which we have written now. So the one point I'm writing now will be the last point. Okay, so while you do this encoding, right? We specify the location of the existing phrase in the dictionary and append the new data. So this in whatever this innovation bit or information bit is there, that is the additional part which you are going to add to some pre-existing or some data which is already existing in your dictionary. I keep building the dictionary as my data comes. Ultimately, that's the goal. Okay, so I can write during the encoding of a new phrase, right? One has to specify the location of an existing phrase. Existing phrase in the dictionary, and what I'm supposed to do, I have to append the new bit or number or any data. It can be letter or whatever. Okay, so this is what I'm supposed to do. So just to brief out, right? I start with the I'm having the data. I try to split the data in the smallest possible size of each group, right? It's a variable size. Initial groups can be size 1, then the size 2 might come, then it might become size 4, all of a sudden it might become size 3, etc. We'll see. Okay, such a way that there is no repetition, first thing. And second thing is that the size should be smallest, as small as possible, right? Once you split that, you try to make a dictionary where you try to keep these data and keep track of a position by means of some numbering. Like if you want to store the data in the memory, most of the time what we do, we give a address and the data. Okay, at this location you have this data, at the next location you have the next data, like that. I create a address plus the data. That's what we call as a dictionary. Okay, so that's the second step. And the finally what we do, you try to do the encoding of that. Whenever we are going for the encoding process, right, what we do, we simply create the code word by adding a prefix. If there is some prefix which is already existing, you use that. If there is not no prefix existing, we will put that as 000. That's the rule. Okay, right. Okay, so the steps are over now. So if explain part comes, you can simply say this. All right. Okay, let's go to the first example. So this is the question. Perform the LZ encoding of the following. So the data set is 1 0 1 0 1 1 0 1 1 0 1 0 1 0 1 1 0. Okay, let me just check this. So 1 0 1 0 1 1 0 1 1 0 1 0 1 0 1 0 1 0. Okay, fine. Okay, so this is the given data. So first step is to split this into variable size groups. So we call it as the LZ parsing. Okay, so let's do that. So I'll start from the first data. I can see that that is 1. So you see this 1 is the individual group because there is no group before this, and the smallest length possible is 1. Okay, then I can go to the next data. It says it is 0. So 0 is also not there, not a previously existing, and the smallest length is 1 itself. So that is a new group. Okay. Then you move next. I have one which is already there. Okay. So I cannot make a group once again containing only one now. I will add its next data. So that is 1, 0. Okay. So I'll try to mark here. So this is over, this is over, this is over. Okay. Move further. In the next one, I can see that it's 1, 1 because it's the, if I take only one, it is already there. 1, 1, it is not there. Okay. The next group should be 0, 1. Then I have 1, 0, which is already there. So I have to go to the next level. So that is 1, 0. Then 0, 1 is already there. So 0, 1, 0 is the next group. Then 1, 0, 1 is already there. So these are the groups. So I just showed how to do that. Now I'll write them. Okay, so this is the first step, number 1. So 1, 0, then 1, 1, 0, 1, 1, 0, 1, 0, 1, 0. Okay. Yeah, so this is 1, 0, 1, 0. So totally how many groups are there? Let's calculate. 1, 2, 3, 4, 5, 6, 7, 8 groups. Okay. So think that you have 8 positions, right? Just think that in order to store them, how many positions you require. If these are the different groups, I just want to assume that I want to store them in the memory, in my computer's memory. I need 8 positions, correct? So this is how you start. So first step is over. Next step is directly creation of my code word. So step number 2, if you see that, uh, I can say that okay, this is over. So phrases are to be stored in a dictionary, right? So I have to create a dictionary in the next step. So dictionary means I should say how many locations I want, right? So my first column will be the dictionary locations. Okay, so I have the following options. You can actually sorry, you can actually start with the decimal numbers also. But anyway, we understood that I need totally 8 positions, correct? So you don't start with the 0. Okay, so position 0 is not going to exist here. Always the position start with number 1, my first position, second position, and so on. Okay, so like that I need 8 positions. So right, what I do, I start with the position number 1, right? 8 means how many binary digits, how many bits you require to write number 8. Not 8 in the sense, starting total 8 positions are there. So you need 3 bits, correct? 2 to the 3 is 8. 8 position, try to write it as a 2 to the power number. Okay, so I have a question. Why only 2 to the power? Answer is because it is binary. Perfect. If it is binary, it is always 2 to the power. Okay, so I need 8 position. So 2 to the power 3 is 8. So you understand that I need to use 3 bits for the representation. Always start with 0, 0, 1 only, then increase. Okay, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now you see how many I have used. I use only 7. Okay, but if you see, I actually have 8 data, correct? No, we don't have to use. That's actually again, you will understand why I'm not using that. It actually helps us in the compression now. Okay, I'll show you the compression happening, but I don't, as of now, just think that I'm not using the 8th value. All right, always, even if you have say 15 values, right, you will write from 0, 0, 0, 0, 0, 0, 1 till 1, 1, 1, 1, one shot. Okay, so irrespective of whatever is a given problem, you follow the same procedure. Start from 1, go till the last possible number. Normally, you will have one shot always. Okay. The next column which we are going to write will be the content or the information. Okay. So when I say I'm trying to write what is called as a content, right? This is the uh, group which we have formed so far. Okay. Every group number will come in the same order. So what's the first data? That is 1, correct? Second group is a 0. The third group is 1, 0. What is the fourth group? 1, 1. Okay, it's in the same order. Then the fifth group is 0, 1. Then the next group, which is 1, 0, 1. Then the next group is 0, 1, 0. Then the last one is 1, 0, 1, 0. Okay, so you can write a dash here saying that I don't need a dictionary location to store this data, right? Something which is already existing. So yeah, that's all, right? So you can see that the why I don't need a location for the last data is because it's something like you can use already existing. Okay, now, so what we are trying to do in the next step is that I'm trying to create the binary code. Okay, I'll write this is the okay. In this case, it is binary code. I don't want to write a word binary because you have the problems which contains not a binary data. Okay, so that's why I'm not writing the binary word here. I can simply write the encoded. Okay, let's call it as encoded data. Right. Normally, you see this encoded data will have two parts. Okay, so the first part I just write in bracket, there will be a prefix. Okay, prefix plus, just now I use the term called innovation bit, correct, in the this thing. Otherwise it's a simple information bit or a innovation bit. Okay, I can write info, some information you want to pass, whatever name they call, let them call, no issue. Okay, it's a the message plus a prefix. Okay, out of which the information is pretty straightforward. Okay, the information directly gets copied as the last bit of your content. So like 1 0 0 1 1 1 0 0. Okay, that will be the information bit for all the 8 rows which I am transmitting, which I'm using. So I can directly write. Okay, so for the first one, it is this is 1. So second one, it is 0. Then you have a 0. Now you see this plus is not addition. Okay, there you are concatenating. Okay, so this is, I'll write concatenation. It's not addition. Okay, I'm not doing any addition. I'm simply concatenating a prefix with the information. So right now I'm directly writing the information below this. So information, how do you copy? It's actually the LSB of the content. So in the content column, look at the LSB, keep writing. Okay, so this is 1, then I have another 1, followed by 1, then you have a 0, followed by a 0. Okay, that is done. So here I need to fill the prefixes. Okay, just to the left side of this data, I just have to fill. Once all get filled, yes, you are ready to go. Okay, once again, how many prefixes you are going to add? Again, that depends upon what type of encoding, in the sense, what is your representation? Binary, yes, you are going to use totally, you are going to add 3 because, right, I have 8 positions, so 3 locations to be added to the left, right? So go to the first data, right? Prefix is actually copied from something which is already existing. Okay, but I see this is my first row. There is nothing, right, that exists before this in my whole table, right? So when you don't have anything, that is directly replaced by zeros. Put sufficiently large number of zeros. I am supposed to put 3 zeros, that's all. Okay, right? So for 0 also, right, 0, do you have 0 before this anywhere? So before this I have only one data, that is 1, correct? 1, it's not 0, so 0 also gets the same prefix, right? When you have null, it's like a null situation. I don't have anything to write over there. Start with zeros. Okay, now you see, I come to the next data. What is the next data? That is a 0, right? Now do you see a 0 before this? Yes. Corresponding to that, what is your dictionary location? Location. Yeah, so your prefix is going to be the pre-existing dictionary location. Location. Okay, so that will be uh, 000. Then do you have the location? This. Yeah. So what I'm going to write now, 001, correct? My sorry, my mistake. I have to look here. Okay, so leave this. Sorry, not here. Okay, I'm not comparing with this zero. I'm comparing with this one. Sorry, my mistake. That's what I was checking. Sorry. Just so for the first two, no issues. Okay. First two, directly you write. Right? It's same. Right. I'm checking that what I have here. Do you have a prefix? No prefix. Do you have a prefix? No prefix. So you add 00000. Okay. Now I'm coming back. Okay. I'll come back. I'll repeat what I'm supposed to do for 10. So for 10, this is my data. I already moved the data to this location. Look at the prefix. Prefix is 1. Do you have, it's already present? Yes. So look at the dictionary location, right? So 001 is the prefix for this particular data. Sorry, no mistake. I already said yes. Sorry, I'm not back to Lempel Ziv. Okay. So what I'm supposed to write here now? 001. Okay. Next, again, I have a 1 here. So that 1 is already existing. Look at its dictionary location. That is once again 001. Correct? So the next data you're going to send 001. Now you see it's not same, right? So the data is different. Encoded data is completely different. So 0011. Now you see I have a data 1, but its prefix is 0. When I see the prefix being 0, 010. Is it fine? As simple as that. So I see 1 is my data, prefix is 10. I can see 10 here. Corresponding to that, you have the dictionary location, that is 011. Right. Next, so next is 01. So 01 means 101. Perfect. 101. All right. Then I have 0 written here. 101 is already there. 101, 110. Okay. So in the sense, instead of, let's assume I may be transmitting or I may be saving the data, okay, into some memory location. So instead of dealing with this data, right, you are going to deal with this data. So that is the encoding chain. So now I have a obvious question that count the number of bits in the original data, that is this data. How many bits you have? Yeah. So you have how much total? 18. 18 bits. Now you calculate the number of bits in the encoded format. So 4 into how many? 4 into 8. So 32. So how can you call it as a compression is my question. Originally it was 18, but now ultimately we can calculate and we can see that we have 32 bits, right? So which is smaller? 18 original version itself looks a compressed version for me. Right? What do you think? Okay, so again, it's not a direct answer, right? You will be able to observe the compression happening only when you deal with a larger data. Now you see, my how many groups I have? I have just some 8 groups. Okay, right? So for 8 groups, right, we don't see any compression that is happening, right? Now you consider a text data that is of 10,000 lines. Okay, Now, whenever you try to do the encoding of that, right, the code which we have generated, right, these codes will be reused again and again, right? I don't have to generate, maybe if you have 10,000, okay, I told 10,000 lines, let me say 10,000 words, right? It's a huge data. If you use a 10,000 word data set to do the encoding, right, you will see that that whole document can be represented within almost, say, less than 5,000 codes. Okay, encoded data will be only 5,000, less than 5,000. Okay, so only when you do that kind of data, like when you use a bigger data set, you will observe the compression happening. Otherwise, this just looks like a encoding scheme for you. Okay, so that's the difference, right? The compression comes into picture only when you use a huge data, right? For a smaller data set like this, we don't observe the compression happening, right? So it looks like I'm actually expanding, not a compressing, right? When this case, but our objective right now to learn the encoding scheme. When we write a, again, for a data set, like when I have a 10,000 words of that, manual calculation is not possible. You have to go for a code. Okay, you have to write a program to do that. But then again, I can calculate a compression ratio, etc., right, by using the appropriate formula. So the general tendency is that whenever I calculate the compression ratio for a LZ, it comes almost 55 to 60%, anywhere between 55 to 60%. That's why I told, if you use 10,000 words, it's less than 5,000. So 5,000 means 50%. Okay, you will be able to represent the 10,000 words with lesser than, right, 5,000 uh, uh, encoded data, 5,000 codes. Okay, so this is your final answer, right, for the given data. This, the last column itself is the encoded data. All right. Okay, now let's go with the, I'll form my next question. So I want to show you how to perform the decode. Okay, so decode the LZ encoded data given below. Okay, so the data is the one which I already have used. I just want to show you that, okay, I'm able to get back my original message. Okay, for that reason, I'll write the same data. Okay, so the same data indicates, okay, what's the first data? 0, 0. So this is the data. Okay, 0, 0, 0, 1, followed by 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, triple 1, 1, 0, 1, 0, 1, 1, 0, 0. Now a bit stream will be given to you, but they have to specify what is the length. Otherwise, it's not possible to go back. So on the transmitter side and the receiver side, they will come to, right. They will be knowing what is the length I should split. Like in this case, it should be 4. Okay, this should be known. Otherwise, see, on the receiver side, the receiver might split it in a different way. Yes, yes. Okay. So you should know the, okay, I'll write in one, if inside the bracket, the, sorry, this is code word length should be known. Okay. In this case, this is equal to 4. Right. So we start again. I will be getting the answer in just 1 or 2 steps. Okay. Very straightforward method. So start with the code word as your first column. So just we'll keep writing this. Okay, I can just copy what I already have. I'll just copy this. This is the code word. Okay. Now, so I'll try to extract my data directly. So this is the, okay, we called it as the info, right? So the info, what I see there, that itself is what I'm trying to extract. So this is the info, right? So what I do, so I know that in the code word, right? It's a binary. So the first three bits are the, they are what? They are corresponding to the prefix, correct? Are you okay? It has to be prefix, right? So once I remove them, whatever remains is your data, correct? Are you okay? So we'll start with that. So I know that the info for the first data is 1. Is it okay? So for the first 1 or 2, you will definitely have to do this. There is no other option, right? It's simply a reverse engineering. I know that I got, how did you get this 0001? 1 was my data. There was a null, prefix was not there. So I added 000, correct? Same thing. So that's what you are going to do now, right? And here I keep tracking of the location in the dictionary. So first location is denoted as 001 only. I know this. So directly you write this. You don't have to do anything. You don't have, you should, it's not expected that you should use some equation or you should know something to write this. No, straightforward. Okay. First position is denoted by 001. That's all. Okay. So all the locations will be in the increasing order, like 001, 010, 011. It will be like that. Okay. So right? I don't have to know something to write this. Okay, right. Similarly, write the second one. What do you write? What is the info? Info is 0. What is the next position? 0, 1, 0. Okay, right. Now, I'll move further. So what I'm trying to do here is, I'll see what is my next info. Info is 0. Right. Okay. Next to that, I have the prefix. Prefix is what? What is the prefix meaning? It's a location, right? Trace out a location, right? 1. So your data is 1, 0. Okay. So you're understanding, right? So we'll do it. We'll do the next one so that it becomes easy for you, right? So I understood that this is 1, 0. So the next location has to be 0, 1, 1. So trace out the next data is 1. 0, 0, 1. So location for 001 is 1. So the data is 1, 1. Very simple. So keep adding. So this is 1, 0, 0. Go to the next data. That is 1. So trace out 0, 1, 0. 0, 1, 0 is here. So 0, 1, 0's information is 0. Now you see the info is not at all repeated. Correct? We are actually doing the reverse of what we did earlier, but it's a pretty straightforward. Okay. Now the next position has to be, it's a 100, so 110. Okay, the next data is, it's 110. So this is 10 and 1 is already there. So this is 110. Okay, proceed further. Then I have the next data is 0 corresponding to 101. I have here. So this is 0, 0, 1, 0. Correct? Okay, so this is 0, 1, 0. Right. So what is the position? This is 1, 1, 1. Right. Then I have the next data as 0. So I need 110 corresponding to 110. It is 10. So that is 1, 0, 1. Right. So yeah. No, no. Location is 110. Correct. See, this is location 110 is the location. In that location, whatever is the information you have, bring it to the prefix position. That's all. Haha, oh, you wanted to go to the previous one? No, not required. I just want the information, right? I wanted to decode, right? See, the decoding happened and this was your message, right? So decoded message is 10101110. Just we need to check that with this. See, 101011. Same thing, right? This data itself has been written over there in the form of a column. So just write this column. So therefore decoded data, right? Therefore decoded data. Keep writing one by one. Don't write it like one in the sense of. Just a second. Okay, so we don't have to write it in any other format. Simply keep writing the yes, one single row. That's all. Like the given data. That's all. Perfect. Right. So the data given is in the same format. So we just have to write that. So this is the overall process of the LZ, Lempel Ziv algorithm. Okay, are you fine with this? Do you have any doubt? No, right? Okay, so let me go with. Okay, so let's go for the next level problem in this. So this binary is pretty straightforward. Okay, so there is a possibility of slightly making this difficult if you go for the quaternary or even higher, right, are possible. So let's go to a quaternary case. So the given, yeah, ternary is also possible. Yes, definitely. Okay, ternary possible. I'll go to the next level. I'll directly jump to the quaternary, right? So this is the given data, right? 1, 3, 3, 0, 0, 2, 0, 2, 1, 1, 1, 3, 0, 0, 0, 0, 2, 2, 1, 2, 2, 2, 3, 3. Okay. All right. So let me count 1, 2, 3, 4, 5, 6, 7, 8, 9, 24, right? Okay. All right. So the procedure still remains same. Okay. So I'll start with the location on the dictionary. So before that, what you will do, you split this, correct? So splitting happens in the following fashion: 1, then 3, correct? 3, 0. Then 0 is not done, so 0 is a single group. 2 is not done, okay? 0, 2 is the next group. 1 is there, so 1, 1 is the next group. 1, 3 will be the next group. 0 is there, so 0, 0 is the next group, okay? 0, 0 is there, so 0, 0, 2 is the next group. 2 is there, 2, 1 is the next group. Am I right? Okay. 2, 1. Then 2, 2, 2, 1 is over. Okay. Then 2, 2. Okay. Then 2, 3, and 3. I don't have any other option. I have to leave it. Okay. Uh, Minimum. There is a rule saying that you should keep it minimum. Length should be minimum. Minimum. If 233 is possible, that's a valid group, but 233 is a not the minimum one as of now. Correct? So like that you have to do this. All right. Okay. So now you think uh, how many positions are required, because it's a quaternary. How many are there? So 13. Okay. How many digits you are going to use? Why 4? Previously, you see, you told that I'm using binary. So 2 to the power. Now it has to be which power? It's 4 to the power. So 4 to the power 1 is 4, not sufficient. Go to the next number. 4 to the power 2. 4 to the power 2 is 16, right? So 2 digits will be used. Okay. Yeah. That's perfect. That's how we calculate. So keep writing the numbers starting from smallest one, 0, 1, right? Then the next number will be 0, 2. Next number is 0, 3. There is no 4, right? Then you have 1, 0. Right, perfect. 1, 0, 1, 1, 1, 2, 1, 3. Then no 1, 4, 2, 0, correct? Right, 2, 0, 2, 1, 2, 2, 2, 3. 1 second, let's count. We needed only 13, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Two more. Okay, just write how many required, only that. Okay, so 2, 3. Yeah, right. 3, 0 and 3, 1. So this is the first column. So next one is the information or the content, correct? So the information, whatever we have, directly write. So that is first one is 1, then 3. This is 3, 0. Next data is 0. Okay. Next data is 2. Okay, I'll show you that. Okay, right. So this is 2. Then you have, I think, 0, 2. Then next one is 1, 1. Then we have 1, 3. This is 0, 0. Then we have 0, correct. 0, 0, 2. This is 2, 1. This is 2, 2, 2, 3. Okay, so directly you are going to write the encoded data. So anyway, now you don't have, previously I wrote, right, this is how you write, prefix plus the information, right? Now you don't have to. Okay, whatever is the code word I can write. I know that only the last digit is what I'm going to write here. So that is 1. So since, right, yeah, so that's what I'm writing. I'll write all together now. So previously I told how to do that. Now you can write in a stretch. So I don't have anything before this. So add 2 zeros, correct? Right. So this is 3 occurring for the first time. So 0, 0, 3. Then 3, 0, out of which 0 is already written here. So 3, I can see 3 is there already. So this is 0, 2, 0. Yeah. Can you tell me the next one? So 0 as it is. So it's coming for the first time. So 0, 0, 0. Right? Correct. Then 2, it's data. Right? So 0, 0, 2. Correct? Then 0, 2. So 2 will be written. 0 is already there. So that is 1, 0, 2. Then 1 already there. 1 is also 0, 1. 0, 1, 1. Then what's the next one? It's 1. No, no, it's 1. 1 means the first position. So 0, 1, 3, right? 0, 1. Then 0, 0, out of which 0 I write. Other 0 is already there. That's 1, 0, 0. Okay. Are you okay? Do you have any doubt? Okay. Next 0, 0, 2. I'll write 2. The 0, 0 do you have? Yes, 2, 1, right? Okay, so that is 2, 1, 2. Then 1 I write here. The 2 already exists. It's 1, 1, 1. Then one more 2, right? There is a 2. So 1, 1, 2. Definitely this has to be 1, 1. Are you okay? Was it fine? Pretty straightforward method to do this. Okay, right? So I hope you are comfortable with this. Take up a problem which is maybe which can be a ternary, right? Up to this level, it can come in the exam, right? But not beyond this, right? Not up to the level 6 or something, because that will have 6 to the power numbers coming into picture. So that's very difficult. Okay, so up to this, it is acceptable. And even if they give, yes, you have enough time to solve in an exam. Okay, so that's why I try to solve for up to this level. All right. So, Okay, so coding part is done. I want you to try the decoding part of this particular question. Anyway, I'm going to share you the document, so refer to that and try to do the decoding. Right? If decoding is, if you feel it difficult, if it is not possible, I'm going to solve that in the next class, and then we are going to move to the next concept.